our next speaker, Jeff Danciger, who's going to be talking to us about proper affine actions by right-angled Coxeter groups.
Okay, thank you. Can you guys hear me in the back? They told me I had to use my big boy voice. Yes, good. Okay, so I'm very happy to be here to speak at this conference in honor of Bill. Bill, as we all know, has played a huge role in defining the subject of locally homogeneous geometric structures on manifolds, as well as other subjects. But what I'm going to talk about today is several types of geometric structures that I think Bill has been very interested in throughout his career. The main player will be affine structures, which is something that Bill worked on very early in his career and has continued to do so. And some of the problems that I'm going to talk about today, I first learned about from Bill, and it's really been, obviously, I think we all know that some of Bill's sort of fundamental geometric ideas have sort of led to all sorts of great mathematics, and it's really been a pleasure to sort of continue that and take some of the ideas that I've learned from Bill and try to push them further and in new directions. Okay, so let's start. Okay, so like I said, the main player is affine geometry. So okay, I need to be able to see what I'm doing here. Okay, so what is affine geometry? It's the GX geometry, where the space X is Rn, and the structure group G is the affine automorphism group of Rn. So what's that? That's all affine transformation. So an element f of aff Rn is any transformation of the form f of x equals ax plus b. Here A is a linear automorphism. It's an element of GLN. And that's what's called the linear part of f. And B is a translation vector. That's what's called the translational part. Okay, great. So I think we've all thought about affine transformations before in some elementary course, but just so that we're all on the same page, I wanted to do a basic demonstration here. Okay, so here is Bill Goldman, thought of as a subset of the plane, R2.
It's usually in R3.
Right. Well, that depends. So now here's the image of Bill after I apply an affine transformation. So this affine transformation rotated Bill and then translated him down and to the left. Of course, there are affine transformations that reflect. This one reflected Bill and then translated him in a different direction. And those are both examples of Euclidean transformations. But more generally, affine transformations can dilate. This one shrunk Bill to half the size. And Bill's favorite affine transformations also include Lorentz transformations. This one stretched Bill along one light-like direction and compressed him along the other one, and then translated. Okay, so obviously there are more types of affine transformations, but any transformations like this and compositions of them are the types of transformations I'll be talking about today. Okay, thanks, Bill, for participating. Okay.
Volunteering.
Right. Let's thank our volunteer. Okay, so the affine group as a group is a semidirect product. It's the semidirect product of GLN with Rn, which is to say that when you compose two affine transformations, their linear parts compose as usual, and their translational parts don't quite add. They add with a twisting by the linear part. Okay. Now the main objects of interest today are what are called proper affine actions. So let's let gamma be a discrete group. A proper affine action is just an action of gamma on Rn by affine transformations, in other words, a representation of gamma in the affine group, which is properly discontinuous. And of course, properly discontinuous actions are very nice because we can take their quotients. So the quotient m equals Rn mod gamma of a proper affine action is a nice Hausdorff manifold, or more generally an orbifold. And of course, such a manifold constructed in this way inherits an affine structure, and affine structures created in this way are actually geodesically complete. So proper affine actions give nice complete affine manifolds and orbifolds, and in fact, the converse is true as well. Okay, so affine geometry contains many interesting subgeometries, and I'm going to talk about a few of those today. One such subgeometry that everybody has studied is Euclidean geometry. This is the subgeometry whose structure group is just the isometries of the standard Euclidean metric. It's those affine transformations whose linear part is an orthogonal transformation. Okay, so how do we make proper actions in Euclidean geometry? Well, here's a well-known example. I can let gamma be z to the n, and I can let each generator act by a pure translation. And provided that I choose my generating translations to be independent, I'll get a nice proper action on Euclidean space. The quotient, of course, is a Euclidean torus. Okay, so here's a picture. This is a wallpaper pattern in R2. It's preserved by a nice proper action by z cross z. Okay, so proper Euclidean actions are very well understood due to famous theorems of Bieberbach from the early 1900s. So suppose that gamma acts properly by Euclidean transformations on some Rn. Then, well, gamma actually must have a finite index subgroup, gamma 0, which is isomorphic to z to the k. Further, if the quotient manifold is compact, then this finite index subgroup, which is a z to the n in this case, acts by translations. So up to finite index, any compact Euclidean manifold comes just from this basic example that I talked about a moment ago. Further, the non-compact case can be understood in terms of the compact case. If the quotient is not compact, there's actually an invariant Euclidean subspace on which the action is co-compact. And the non-compact Euclidean manifold M is actually a flat orthogonal vector bundle over this compact submanifold of lower dimension. Okay, so we'd like to have an analog of these theorems in affine geometry. So the basic questions that will motivate what I'm talking about today are questions you could ask about any geometric structure. One, which discrete groups gamma admit proper affine actions on some affine space Rn? So what are the groups that are able to act properly in this geometry? And two, which manifolds and orbifolds do we get as quotients by these proper actions? Okay, so this is perhaps the fundamental question, or one set of fundamental questions about any GX structure that you could ask. Okay, so of course Euclidean, the proper Euclidean actions I just talked about are examples of these. How much more complicated can it get when we're allowed to use more general affine transformations? Okay, so more examples include, well, there are affine nil manifolds. There are nil manifolds that emit affine structures. So maybe the easiest example is the three-dimensional Thurston geometry called nil. That's actually the same thing as the Heisenberg group. So any three-dimensional manifold with nil geometry is actually obtained by a proper affine action. And a side note that I wasn't aware of until recently, but there's a really cool theorem about these affine nil manifolds due to Bill and Hirsch from the early 80s. In fact, a compact affine manifold admits a polynomial Riemannian metric if and only if it's virtually a complete affine nil manifold. So that's kind of a cool result. Polynomial Riemannian metric is a metric whose coefficients in any affine chart are polynomial. So if you have such a structure, then you're actually an affine nil manifold. More generally, though, there are affine solved manifolds. For example, the three-dimensional Thurston geometry Sol is a subgeometry of affine geometry. And so there are many examples of affine manifolds which come from lattices in solvable Lie groups. Okay, so how much more complicated can it get? Okay, so there's a famous conjecture about this, which goes back to the work of Auslander in the 60s. It says that suppose gamma acts properly by affine transformations on Rn, and such that the quotient is compact. Then gamma ought to be virtually solvable. In other words, gamma has a finite index subgroup which is solvable. Okay, let me just say before discussing this statement, it's now known to be true up to dimension 6. Bill, together with David Fried, proved it in 83 for dimension up to 3. And more recently, Abels, Margulis, and Seufer have a proof up to dimension 6. In larger dimensions, it's still wide open. And I think it's quite a challenging and interesting question. I don't know whether or not it should be true, but maybe you should ask Bill over a beer about that. Okay. All right, so this statement that gamma is virtually solvable in this setting is equivalent to the statement that gamma does not contain a non-abelian free group. So free groups we think of as being pretty big. They grow very rapidly, whereas solvable groups are somehow smaller and less complicated. So the intuition maybe behind this conjecture is that, well, affine geometry is more flexible than Euclidean geometry, yes, but it's still a flat geometry, so there shouldn't be enough room inside of it for big complicated groups to act properly. Right? It's flat. And that sounds reasonable. However, things are slightly more complicated than you might first imagine, because in fact, in 1983, Margulis discovered that non-abelian free groups do admit proper affine actions in dimension 3. And the quotient manifolds coming from these actions are now popularly known as Margulis spacetimes. So let me give a definition. A Margulis spacetime is a quotient M equals R3 mod FR, where FR is a non-abelian free group acting properly by affine transformations. And indeed, these are called spacetimes for a reason. It actually follows from the work of Fried and Goldman in their proof of the Auslander conjecture for dimension 3, that any such action has to preserve a parallel 2-1 inner product on R3. In other words, Margulis spacetimes are actually they actually have a more specific structure. Thank you. That is, they're not just affine. They have a flat Lorentzian metric, a complete flat Lorentzian metric. So indeed, they are spacetimes. Okay, and in case it wasn't clear, it's important to note, Margulis spacetimes are not compact, so they're not counterexamples to the Auslander conjecture. Why are they not compact? Well, free groups are one-dimensional. They have virtual cohomological dimension 1. And 1 is less than 3. And 3 is what you would need in order to have a co-compact action on R3. So if you had a discrete group acting properly and co-compactly on Rn, it has to have virtual cohomological dimension n. Okay. Nonetheless, I think the discovery of these examples really makes you wonder about whether or not the Auslander conjecture is true. And I think they were certainly quite surprising when they were discovered. Okay. So in case you haven't thought about these things before, it sounds kind of weird at first. How on earth are you going to make a non-abelian free group act on R3? I mean, what does that even look like? So Todd Drum, one of Bill's students and tireless organizer of this lovely conference, came up with a very concrete construction that he used to construct many new examples of Margulis spacetimes. And he used these polyhedral surfaces called crooked planes. So let me just show you what those look like. Here's 4 crooked planes, and I'm going to try to move them around so you can see them. Okay, so these are surfaces that separate R3 into 2 components, and they're well adapted to the Lorentzian geometry. And one of their most important features is that they have the ability to be made disjoint in R3. So these 4 are actually not touching each other at all. I hope you can see that. So you can actually play ping pong with these surfaces in R3 and construct proper actions by free groups via ping pong in a very explicit way. So this is pretty cool. Todd and Bill thought about these in the early 90s, and one thing they observed is that, well, because this is so explicit and you're sort of making this manifold by gluing together a polyhedron, the topology of the quotient is clear. It's a handle body. That's not necessarily clear for all Margulis spacetimes. The reason is they could potentially fail to be tame. So Todd and Bill formulated a conjecture that all Margulis spacetimes should be tame, and stronger, perhaps they should all be made out of crooked planes, out of fundamental domains like this. And that conjecture has led to lots of interesting work about Margulis spacetimes and affine geometry. And I wanted to just say a few things about how far our state of knowledge has come about these objects since those conjectures were made by Bill and Todd in the 90s. Okay, so first of all, we now have a very good understanding of what it means for an action of a free group by affine transformations to be properly discontinuous. Let me not go through all the work on this, but essentially it has to do with positivity of these translation lengths that we call Margulis invariants. Okay, the topology of Margulis spacetimes is now understood. They are all tame. They are all diffeomorphic to handle bodies, and that was only resolved in the most general case very recently. Further, they do admit crooked plane fundamental domains, so they're geometrically tame, if you want to call it that. That was also resolved recently. And something nice that you can also say about them is that they fiber in time-like lines over non-compact hyperbolic surfaces. So geometrically, they, to some degree, look like a non-compact hyperbolic surface in the spatial directions, and time-like geodesics in the third direction. Okay. They also have a very rich moduli space. The moduli space is naturally a subset of the tangent bundle of the Fricka-Teichmuller space F of non-compact hyperbolic surfaces. The fiber, so the Margulis spacetimes associated to a single surface S, is an open convex cone in this tangent space. And in fact, it has a very nice combinatorial structure. It can actually be, this fiber can be identified with the arc complex, or actually a subset of the arc complex of S. In particular, we can construct very explicitly all Margulis spacetimes. We can tell you how to make all of them quite explicitly. Okay, so a lot has been done, and you'll probably notice that yes.
Can you realize this non-compact hyperbolic surface as a maximal hyperbolic space-like surface?
No, I don't think so. They're not globally hyperbolic, so yeah, I can tell you more about that later. Okay. Anyway, I don't want to say more about these Margulis spacetimes, but of course, if you take a look at this list of literature here, you see Bill's name all over it. He's, him together with various collaborators has really pushed this, the understanding of these very interesting, strange objects to the point where we now have the ability to understand them very well. Okay. So thanks, Bill. All right. So what about other proper affine actions? So various people have studied proper affine actions by free groups in higher dimension. Albers, Margulis, and Seufer have studied the case where the linear part is in the orthogonal group of some indefinite quadratic form, and showing that Zariski-dense proper affine actions do happen in certain dimensions. Ilya Smilga has studied the case when the linear parts lie in adjoint representations of semi-simple Lie groups. That's actually the case that I'll talk about later in the talk. That's the sort of setting where we'll construct some new affine actions. Okay. So one strategy towards the Auslander conjecture might be to understand all possible proper affine actions by free groups, and then try to rule out the possibility that any of them could be part of a larger co-compact proper action. Maybe if you understand them well enough, maybe you could show that there's really no way to fit them together to make a co-compact action in Rn. Okay, that's probably pretty hard. The reason is, I've only mentioned a few cases where these free groups exist. There's many more. And in each of those cases, there's what appears to be a complicated moduli space of possible proper affine actions there. So there's very little understanding of those moduli spaces, and it took quite a bit of work to even understand the situation in R3. And at least the way I see it, there's not much of an obvious extension of those ideas to these higher dimensional settings. Well, at least not all of them. Okay, so what if you want to find a counterexample to the Auslander conjecture? Well, you shouldn't look at free groups. They're one-dimensional, so they have no chance of acting co-compactly, as we discussed before. So what you'd really like is to find interesting, non-solvable discrete groups that emit proper affine actions that also have large virtual cohomological dimension. So so in fact, there's been a lot of work on free groups, but we know relatively little about any other types of interesting non-solvable discrete groups acting properly by affine transformations. In fact, until, I'll tell you in a moment, it wasn't even known whether a hyperbolic group of higher cohomological dimension is able to act properly by affine transformations. Okay, so that brings us to the main theorem. So this is joint work with Francois Garreteau and Fanny Castle. We actually proved that, there's actually a large source of interesting discrete groups that emit proper affine actions, and that's the class of groups, the right-angled Coxeter groups. So we show that any right-angled Coxeter group, which I'll probably write as RACG from now on, emits a proper affine action on some Rn. And here the dimension of the affine space is k choose 2, where k is the number of generators of the Coxeter group. Okay, so these are they're not co-compact, they're not counterexamples to the Auslander conjecture, and in a sense they're very far from being co-compact because, as you see, the dimension of the affine space is quadratic in the number of generators, and the number of generators is a trivial bound for the cohomological dimension of the group here in this setting. But we still do get a lot of interesting proper affine actions by groups that previously we didn't know whether they could emit such actions. So, for example, the fundamental group of any closed surface, a surface group, emits a proper affine action because a surface group, for example, is a subgroup of a right-angled pentagon group. The fundamental group of any hyperbolic 3 manifold emits a proper affine action because by the virtual specialness theorem of ANGLED, those virtually embed in right-angled Coxeter groups. And further, we get Gromov hyperbolic groups of arbitrary cohomological dimension. And this follows from work of Januszkiewicz and Kwiatkowski, showing that there exist right-angled Coxeter groups which are both hyperbolic and have arbitrarily large dimension. Okay, great. Are there any questions about the statement? Okay. Yeah? Okay, so I want to show you how to construct these things. Okay. So first, let me remind you what a right-angled Coxeter group is. So it's a group, I'll call it W, generated by k involutions, gamma 1 up to gamma k. So they're k generators. Their squares are 1, so they all have order 2. And for some pairs, but not necessarily all pairs, you can add an extra relation that gamma I commutes with gamma j. Okay, so here's a simple example that I'll use to illustrate the construction. Let's just take this right-angled Coxeter group. It's generated by 3 generators, gamma 1, gamma 2, and gamma 3. Each of them have square equal to the identity. And let's impose one further relation that gamma 1 and gamma 3 commute. But we'll impose no relation between gamma 1 and gamma 2, nor on gamma 2 and gamma 3. Okay. So why are these called right-angled Coxeter groups? Well, really, you're supposed to think of these abstract groups as reflection groups. So this group actually can be realized as a reflection group in the hyperbolic plane. So let me draw a picture of that. Okay. So here's the hyperbolic plane. And I want to think of it as the round disk inside of RP2. I want to think of it in the projective model. Okay. And so now I'm going to draw a fundamental domain. Okay. Okay, so here's a triangle. It's some of it, 2 of its vertices are outside the hyperbolic plane. So in the hyperbolic plane, these 2 faces meet at a vertex. This third face doesn't touch. It's ultra parallel to the other sides here. Okay. So now I'm going to construct an action of this group on the hyperbolic plane by reflecting this triangle. So what I'm going to do, I let gamma 1 reflect in this side. I'll let gamma 2 reflect in this side. And I'll let gamma 3 reflect in this third side here. Okay, so you see that if I apply gamma 1, so I reflect like this, and then I apply gamma 3, so I reflect like this, I get the same thing as if I reflect by that I reflect by gamma 3 and then by gamma 1. So that's the commutativity. Having this right angle here enforces the relation that gamma 1 and gamma 3 commute. And it's reasonably easy to see that there's not going to be any other accidental relations in the group generated by these elements. And in fact, we're going to get a nice discrete embedding of our right-angled Coxeter group in the isometry group of the hyperbolic plane, which I'll think of as O21. Okay. Now, I say here there's a family. In fact, there's some choices in this construction. So because the second face and the first face don't meet, there's actually a parameter here. There's a distance, which I'll call D12, between the first and second face, and I can choose that distance. Similarly, the hyperbolic, shortest distance between the second side and the third side is some number. It's D23, and I can actually move if you like, I can keep the first and third walls fixed and move the second one around to change these distances to be anything I want. And if I do that, that gives me a whole family, a 2-parameter family of discrete embeddings of W in O21, which are really a non-trivial family. They're different. They're not conjugate. OK? Great. So This is good because it turns out that there's a very simple way to take deformations of a discrete embedding of your group in a Lie group and turn that into an affine action. So let me explain how that works. Okay, I think we understand this. So delta, I'm going to call this fundamental domain here delta. Maybe I should draw one more. So it's hard to draw this in the projective model. But if you reflect on this side, you start to go in this direction. And similarly. And once you apply the entire group, you see a nice tiling, actually, of a convex region of RP2, which contains the hyperbolic plane. And the group acts discretely on this tiling. All right, so how do we get an affine action from a deformation? OK, so I'm going to choose one of these discrete embeddings and call it rho 0. Now observe that W acts via rho 0 on the space frac X of vector fields on H2. OK, so that's some huge infinite dimensional vector space. But nonetheless, the action is obvious. In symbols, it looks like this. But intuitively, it just means you pick up the vector field and you move it with the isometry corresponding to gamma under rho. OK? All right, so it's in this big vector space that I'm going to find some affine subspaces where we can construct nice affine actions. OK, so so first observe that this action, even though this space of vector fields is huge, there's a nice finite dimensional subspace. It's the Lie algebra of O21, thought of as the killing vector fields. These are the vector fields on H2, which to first order preserve the hyperbolic metric. They're infinitesimal isometries. And this action that I've written down here is when restricted to the killing vector fields, it's just the adjoint action. OK? All right, great. So now let's give ourselves a path. So if I have a family, rho T, of representations based at this first one that I chose, maybe you can believe that I get a family of homeomorphisms from H2 to H2 that describe the deformation of this tiling. I changed these generators a little bit. Maybe I changed the shape of this fundamental domain. The tiling deforms along with that change, and I can actually realize that deformation by a path of maps, Ft. And I can take its derivative. And that gives me a deformation vector field, which describes this the change in geometry to first order of the tiling. OK? Great. So X is not invariant under the action. It's not fixed by the action of rho 0. But it's automorphic, or also known as U equivariant. In the sense that when I pick it up and move it with an element of the group, what I get is the same vector field back plus an infinitesimal isometry. In other words, if I look at this deformation from the point of view of a different tile somewhere else, well, locally I should see the same thing happening, but globally there might be some isometric drift. So, relative to the other tiles, I'm moving in the same way. But globally, I might be moving by some infinitesimal isometry. OK, so this function u is what's called the Deprivation Co Cycle. It's essentially the derivative of this path of representations. It's telling you how the group elements are deforming under this path. OK, great. So if I take the coset of the Lie algebra associated to x plus little O21, that's an invariant affine three-dimensional subspace. OK. So and that's where we're going to see a nice proper action. So for any deformation vector field associated to any infinitesimal deformation, there's some three-dimensional affine subspace inside of this large vector space that's preserved. OK? Is that clear? I hope that's clear. OK. Now, okay, so you don't actually need the vector field to see this action, really. I mean, if you look at what the action is doing, it's essentially, if you take x plus v, it takes it to x plus add rho of gamma times v plus u of gamma. So if you want to forget the vector field and just think of this action as being an affine action on the Lie algebra, that might be more convenient for you. That's usually what we do in our papers, but I find this picture nice for intuitive reasons. Okay. So what does this action look like? So there's actually a really nice connection between the way that the hyperbolic geometry is deforming and the way that these affine transformations look. And this is a connection that was, I believe, first observed by Bill with Margulis in a paper, I think, from the 90s. And the connection is this. So if I look at a hyperbolic element, rho of gamma, it has some translation length, L. This affine action comes from a deformation of rho. So that translation length is changing by some amount t. Now, the affine action, what you see hyperbolic dynamics in two directions, some expansion and contraction. But you also see a linear translation along some fixed, some invariant line by an amount t, which is the same as the change in the length L over here. So essentially, if you want to get a proper action, well, you're going to need the translation lengths to be non-zero. So you're going to be wanting to change the lengths of the hyperbolic elements in your group. And indeed, it turns out you want to change them all with the same sign. This translation length has a sign, and you need them all to change positively or all to change negatively. Okay, so let's make an example of a proper affine action. Okay, what I'm going to do, so following the intuition that I just said, I'm going to set my two parameters to be some constant capital D minus t. So basically, I'm going to be moving this second wall in towards the first and third wall at some rate. Okay, so I'm trying to shrink these tiles, hoping that all of the lengths will get shorter. All of the hyperbolic translation lengths will get shorter. Okay, so I do that. I get this infinitesimal deformation u, which has a very nice interpretation in this group. If you apply it to a generator, it's actually telling you the motion of the reflection walls. So in this particular example, maybe I've normalized so that these walls don't move. This second wall is moving, and this deformation Co cycle tells me exactly how. So it's moving, as I said, I've arranged for it to be moving inward. Okay. And similarly, these walls are moving inward. So the tiling is shrinking. And if I go to a tile out here, well, it should be shrinking, but this wall is already moving this way. So these two walls have to move even faster towards the center of the picture. So essentially, what you see is all tiles are shrinking relative, that the walls are moving together relative to themselves. But if you go far out in the tiling, because they're all shrinking, the farthest tiles have to move very rapidly towards the center of this picture. Okay, so this type of contraction gives us a nice proper action on the affine side, affine geometry side. Okay, so as I just explained, this vector field is what's called uniformly contracting. Points far away from the center are moving very rapidly towards the center. And that's what's going to allow us to prove this special case of the theorem. The affine action of W on the vector field x plus O21 is proper. And I'll give you a formal argument in a minute, but it's clear, right? The action is, of course, just to pick up the vector field and move it along the tiling, right? This picture of x, this vector field focuses on this point, right? And very far away, the vectors are huge. because these tiles far away have to move very rapidly for all the tiles in between to shrink. So if I start moving this vector field around with a big element of the group, this point of focus goes far away, and now in the middle of the picture I see gigantic vectors. In other words, the action has changed the vector field by an enormous amount. So intuitively it should be proper. Okay, how do we formalize that? For the sake of the argument in the general case, let me say that. Okay, so we consider any x plus v. So I take this vector field and I add an isometric vector field to it. It's still uniformly contracting because the isometric vector field I added didn't change this contraction property. 2 points far away are still moving close together. They might both be moving together in some new direction, but relative to one another, their distance is shrinking. So there's one tile, rho alpha delta, which moves least or slowest under this x plus v, under this vector field. So in other words, if I add a killing field to this picture, it just refocuses somewhere else on some other tile. Okay? So I simply map this point of my affine space to this tile. And this gives me a sort of coarsely continuous projection from the affine space in question to the collection of tiles of this tiling. It's equivariant, which is pretty easy to see. And therefore, properness of the action of the group on the space of tiles, that's proper, implies properness of the action upstairs on the affine space. Okay? In other words, the affine action sort of coarsely fibers over this tiling. Okay? Are there any questions about that? This is.
How do you measure what is the slowest?
Yeah, pick a point in the center of each tile, and just look at its vector, and ask for the one which is smallest. There has to be one, and it's got to be unique, up to maybe there being a tie between two adjacent tiles or something like that. Yeah. Yeah, I didn't say. It's been a little loose about how this vector field is constructed. But.
So if you think of this as the Dirichlet fundamental domain, then the center will be the center. I'm just trying to see how to choose the center.
Just choose a point.
Just choose a point.
Yeah, just choose it and then orbit it. Yeah. In fact, it turns out that, I've been doing things in a sort of coarse way here, but it turns out you can make these deformation vector fields in this example, and more generally for Margulis spacetimes, you can do this as well. You can make the vector fields actually contracting even not coarsely, but even I don't know what to call it, actually contracting. So you could decide to pick the point of this vector field, which is the 0. So this vector field will actually have a 0 in some tile, probably not at the center, and you could project to H2 in that way. Yeah. So yeah, upgrading this constroction to give a projection to the hyperbolic plane is how we prove that Margulis spacetimes have these fiberings by time-like geodesics, fibrations by time-like geodesics. Yeah. Other questions? Okay, so this idea of contraction, this picture, is sort of one of the main ideas that has gone into my work with Fanny Kessel and Francois Garreteau on Margulis spacetimes. It turns out that this is not a Margulis spacetime. It's not a free group, but virtually it is a free group. And it turns out that any proper action by a free group comes from one of these contracting vector fields. That's something that may not have an analog in higher dimensions. Okay. Okay, so I want to talk. How much time do I have? Okay. I want to talk about the general case now. So let's let W be any right-angled Coxeter group with, say, k generators. I want to do the same thing, right? So I need some family of representations that I can deform and try to get affine actions from. So in fact, there's nice families of discrete faithful linear representations of W, which are associated to convex projective structures. Sort of one nice such representation is called the canonical representation. It was described by Titz, I believe. And there's a very nice general theory of linear reflection groups due to Wimberg. Now, the representations that I want to look at now are deformations of the canonical representation that were studied by Kramer and by Dyer, Holweg, and Ripple more recently in the setting of Katz-Moody groups. OK, so how does it work? So the idea is similar. You start with a polyhedron or a polytope. And you want to act on it with W. So you let each generator act by reflecting, doing some projective reflection across a face. And if you do this just right, the orbit of this polytope under all these reflections will be a nice convex domain in projective space. And the action of W will be nice and properly discontinuous and preserve a tiling by copies of this polytope. OK. So we can do this. There are constructions of this, which I'll describe right now. They're very explicit. One way to do it is, so if we're going to work in RK. Remember, K is the number of generators. And for each non-commuting pair, gamma I and gamma J, I'm going to choose a parameter, Dij, greater than 0. So the analogs of these distances that I chose in the hyperbolic plane here. OK, write down a bilinear form B whose coefficients depend on these parameters that I chose. And then I use B to construct a polytope, delta. And the faces of delta are the orthogonal complements of the standard basis vectors with respect to B. And by the way we've chosen the coefficients of B, we see that for generators that commute, their corresponding faces meet at right angles. So we have a hope of getting a nice tiling like we did before. And in fact, it does work. You simply use B to define reflections in these faces, which gives you a representation of W into the orthogonal group of B. And it does preserve a nice convex domain tiled by copies of delta. So the representation is discrete and faithful. And of course, it can be deformed by choosing different parameters, D. OK, and let's call the convex domain omega. OK, so yeah, so from this construction, we already get lots of affine actions. We can take any infinitesimal deformation tangent to this family, and we get some affine action. But figuring out which, if any, of those are properly discontinuous is, of course, the hard thing. So to do that, we need to be able to control the geometry of these representations. And the way we did that in the basic example is we had the hyperbolic plane to work with, and we could use this nice Riemannian metric space to tell us about the affine action. Unfortunately, the signature of this bilinear form is not always going to be Lorentzian. We don't have any control of it, really. So it's just going to be some PQ plus 1. So we may not have any hyperbolic geometry to work with. But what we do have is a generalization of hyperbolic geometry. So the natural geometry here is what's called Hpq geometry. It's the pseudo-Riemannian hyperbolic geometry of signature PQ. And it's realized in projective space as the negative lines in RK with respect to this bilinear form B. OK, so here's a picture. This is a picture of H21. Let me actually draw something. So in the case that PQ is 2, 1, you get a picture like this. the pseudo-Riemannian hyperbolic space H21 is actually also known as ADS3, which is one of my favorite geometries. And it's the interior of this projective quadric here. Now this orthogonal group, in this case O22, preserves this space, and it preserves an invariant metric on it. But that metric, as I said, is not Riemannian. It's signature 2,1. And for the purposes of this talk, all you need to know about that metric is it can actually be defined in terms of Hilbert geometry. In particular, if you take 2 points such that the line between them intersects this quadric in 2 other points, then this distance is positive. If you take 2 points such that the line between them does not leave the quadric, it actually closes up inside of this quadric, then the distance here is negative. And if you take, let's say, it's supposed to be tangent. 2 points such that the line between them just barely kisses the boundary, this quadric, then the distance between them is actually 0. Okay, so you can imagine that trying to work with this geometry and do the same types of things that you do in Riemannian geometry is quite difficult. Some things just don't work, and it can be quite ugly to work with this. But on the other hand, it has a lot of similar properties to hyperbolic geometry. It has a lot of negative curvature properties, and the types of group actions that we're looking at can actually be very nice. Yeah. So let's see. So here in this picture is now a copy of a fundamental domain, delta, which is sitting inside of H21. I now take its orbit under this reflection group. These parameters Dij that I chose are the distances in this geometry between the faces. And I can take its orbit. I see this nice convex hull which appears, this nice convex domain which appears. It turns out that because this Coxeter group is Gromov hyperbolic, this is actually a reflection group this is the right-angled hexagon group here. I should say I've cut off. This is the same picture as I showed 2 slides ago, but I cut off some parts of it so that it fits nicely into H21. I take its orbit. I see this nice convex domain that's tiled by these polyhedra. That's called omega, and that's the geometry that we're going to work with in order to get our proper affine actions. Okay, so yeah, you should be reminded of, this kind of looks like a convex core of like a quasi-Fuchsian group in hyperbolic 3 space. Indeed, there's a lot of similarities between certain representations in Hpq geometry and quasi-Fuchsian representations. And you'll hear more about that in Fanny Castle's talk tomorrow. Okay, so what do we do, just to finish up? Okay, so I'm going to choose my parameters, Dij, again, to all be shrinking. So remember, these are the distances between faces that are not meeting at right angles. From that, I get a family of representations, and a tangent to that family, u, the derivative, which is an infinitesimal deformation, and associated to that is a deformation vector field. Okay, let me show you how this looks. So here's what the deformation looks like. Can you see that? Okay, yeah. So I'm deforming it. Oh, whoops. And you see it's on the one hand, it's sort of shrinking in the time direction and kind of also spreading out in the space direction. So you have to learn how to look at these pictures, but you can sort of see contraction going on there. Okay, so the main theorem is that the row zero action on this particular affine space, which is a copy of R k choose 2, is proper. And the proof is very similar. This vector field x, you might imagine, is contracting, but it's actually only contracting in positive directions. So it turns out we can't control what the geometry is doing in negative directions. That turns out not to matter because every fundamental domain or tile in this tiling sees all other tiles except for maybe finitely many in positive directions. In this picture here, you can see the limit set I've drawn around this one tile. It's seeing the limit set in positive directions. In fact, in a compact family of positive directions. So if we just look at what the vector field is doing, only in those compactly many positive directions, then we actually can prove that some tile row alpha delta moves slowest. Okay, and so we get our equivariant projection from this affine space to the space of tiles, showing that the action is proper. Okay. Okay, so I'll just finish up now with a few questions. So again, these proper actions are made by these coarse projections. So in particular, we don't see any nice fibrations, and we don't see any nice fundamental domains. So it would be, I think, really nice to know what the analog of crooked planes might be for these types of affine actions. I don't have any idea what a nice fundamental domain might look like, if they even exist. The next question, which infinitesimal deformations U give proper actions? So what does the moduli space look like? I've constructed basically one proper cocycle, U. What does the space of all of those proper cocycles look like? It might be an interesting moduli space to study. And then finally, as I said before, this construction gives a proper action on an affine space whose dimension is at least quadratic in the virtual cohomological dimension of W, probably bigger than quadratic. Is there a way to cut down the dimension? Is there a way to get close to having a counterexample to the Auslander conjecture with a similar construction? I don't know. Okay, and I'll stop there.
Are there any other questions? Yeah.
So are your actions A?
I don't know. I think they probably are, but because we only have these coarse projections rather than actual fiber bundle projections, it's not immediate that they are. But I think it might be possible to show that they are even using the coarse projection, but I don't know. Yeah. JP. Yeah.
What's the part where the fact that the groups are right angled? Where is that crucial? Like, could you possibly do this with other Coxeter groups?
So that's a good question. You can't do exactly this with other Coxeter groups. The reason that it matters that they're right angled is because you have this freedom. Oh, this is going to take forever, sorry. Oh, yeah, there it is. You have this free parameter here in the definition of this bilinear form, which essentially says if there's no relationship between two generators, you're free to say how far apart their walls should be. If there is a relationship, if, for example, gamma I, gamma j should be order 7, then they need to meet at an angle 2 pi over 7, right? So you don't have any freedom to deform the representation. here, the only collections of generators where there's no freedom to deform, they only generate finite subgroups. But if you can imagine if there was a copy of the 237 triangle group in your Coxeter group, restricting to the subspace generated by those by the dual vectors to those generators that would be a rigid subspace. There'd be no way to deform that, so you couldn't get contraction, so you have no hope. Yeah. So this doesn't work, but as a consolation, there's a theorem of Hagelin and Wise that any Coxeter group virtually embeds in a right-angled Coxeter group. So you do somehow get any Coxeter group, proper affine actions of any Coxeter group, but they might be, I don't know, they're very not constructible, I think.
Yeah, okay, if you didn't have those sort of triangular groups.
Yeah.
Phi component, if you didn't have any finite subgroups. If any infinite group had infinities in it.
Exactly, yeah. But I think the only way that, well, right, you might be able to throw a few like 3s in there or something, but yeah, essentially you need to have freedom to deform when you have anything that's going to generate an infinite subgroup. Yeah.
Specifically for the pentagon?
Yeah.
So has the surfaces in it? So, I mean, what do you think is the lowest dimension in affine action? I mean, you get 10 of this, right?
Yeah, yes, you get 10. So actually, I don't know about the pentagon, but this picture I've been showing you is actually, so you may have noticed this picture is in dimension 3, but it's a right-angled hexagon group. So it should really be in dimension 15, according to the construction that I made. But sometimes, if you choose the parameters just right, everything collapses into a smaller subspace. And in particular, in the case of a right-angled 2n-gon, we can construct very explicitly in H21 or in H3 contracting deformations of these groups. So for surface groups, or more generally right-angled 2n-gon groups, we do get proper affine actions in dimension 6. Yeah, can you go lower than that? I really doubt it, but I don't know. Yeah.
Any other questions? Well, let's thank Jeff again. And we resume at 4.